Okay, welcome. And as you can see in the title, I will talk about translation. What are your ideas about translation? What do you think about translation? What does it mean? Shout out, please.
Changing from one thing to another?
Yes, translation is changing from one thing to another, but what does it mean? For example, from one language, a spoken language, to another spoken language. But if we can also think about it like we translate from a computer language in a text form into something, a binary form. So we speak about translation units and we speak about compilers. All of this means translation. So I will speak about a couple of things. We go from the beginnings of a machine to an experiment in the end. And this particular machine that I want to speak about is this machine here. You probably have no clue what it is about. It is about something that we built in our company. And in the company, I'm an electrical engineer and I do a lot of stuff in there. And what this machine does, it looks at wheel axles. And what a wheel axle is, this is the orange colored piece of a train wheel, and this is a look into a freighter depot in a company in Germany. And this is not what we are looking at right now. What we look at is these kind of things, personal passenger trains, and here you find the wheel axles in a passenger train. And in the bottom you see the geometry is way more complicated there than it is in a freighter train. And on both ends of the wheel axles you have holes, and into these holes you can put sensors in there, and we inspect these wheel axles for cracks or holes or something like that using these sensors. And as you might imagine, we are not allowed to destroy these axles. We do it in a non-destructive way. Okay, so this is the stuff that you want to do with this particular machine. The company is 15 years old right now, and so the founding story of this company is actually this particular incident or accident in Germany. It was at the past year in the last century where the biggest train accident happened in Germany. And this was the idea. We need to do more thorough inspections of wheel axles, and we have to found a company who can do that without asking particular people trained for something. We want to do it with a machine so that you get off the hook and no longer be sued by such kind of accidents. And if you look on these pictures, you will see these wheel axles in there. So this was the reason why this machine came into existence. And this was the year 2009 that the company was founded. And this is where the story begins. It begins with a lot of strings that they have to create during the execution of a program. Sometimes it's the string itself, sometimes it goes into a UI, something like that. But in the beginning we were pretty humble. We only were supporting German. And the best thing to do, string concatenation and or putting pieces together, was boost format. It has a couple of reasons why we do that, but on the bottom you see it's quite easy to use. We have in the left a formatting specifier. This is just a string on particular information on top of that, and then we concatenate a couple of arguments that you can put into these strings if we happen to have formatting specifiers in there. So we have a separation between the string and the arguments, and these are concatenated by a couple of function calls. Here, these are the operands in the percent operator. So let's move on. 5 more years, and we had a trouble for the first time. We became too successful. We had customers from outside the German-speaking world, and now we had to think about what to do next. We could no longer afford to print everything in German. We could no longer put all the German strings into our code. We had to find a way to do it more programmatically, and also to give the customers the option to choose between languages. So the first language we had to support was Czech. And as always, the best way to do, look at Boost, and Boost has something called a library Boost Local. And with it came the question of how to handle string translation. The questions have been, which translation system should we use? Are there mature translation systems there? Is there an ecosystem around them, in particular editors and a build system? And does it fit into our existing code? Does it feel natural? But the most important question has been, we must not forget our end users, because the end users who would probably supply some of these translations are in no way any domain experts in their domain, but not in our domain. And they, for the most part, don't even have an idea how IT works. So when it comes to what kind of format would we have to supply to them, it can obviously not be a binary format. XML might be something that is pretty popular in translation systems, but XML has strict rules about how the tables should look like. And there is something similar with JSON. JSON is more relaxed, but still prone to errors for people who are not familiar to JSON. So in the end, we came up with the idea, okay, let's do it as text files, and this is what we actually also find in the library called getText, and this is what we were using to do the translation at runtime. We have a C implementation. This is coming from GNU, the getText library. This is pretty old and pretty common. You find it pretty much everywhere. And Boost Local is using the same kind of thing. It's actually an implementation of the same algorithms that you also find in getText. And what these libraries revolve about is message catalogs. Message catalogs are the collection of translations in a particular language or a particular domain. And so the message catalogs, the handling of these message catalogs, loading, unloading, selecting, all this kind of stuff is the back end that you have in such a library, and the actual individual translation that you need during the execution of your program are considered the front end of this system here. And as it turns out, in the beginning of this year, GNU getText, or the getText by itself, became standardized. So it was a good choice to actually do this in our company. And probably, if you're interested in this kind of stuff, you probably should do the same as well. And it comes with a couple of tools. First, you need to mark all these strings in your program as being translatable. And how you can do that, yeah, we see in the example before. Now you say, okay, this particular string needs to be translated. And you have more tools. One of them scans our source files. You have a collection of them. You say which prefixes or markups you use in your source code. And the output of this scan process of all your source files is then a file called a PO file, which is language agnostic and is a transient kind of thing. Every time you scan your sources, you get such a kind of file. And you now have more tools in the gettext ecosystem, which is actually doing the translation process with the help of the customers or the developers. And what you do, you take these extracted strings that you want to translate, and now you look for which country or particular region or even a company you need to please to get a particular translation for. We had customers where a particular target company was asking for particular translation. And you have a couple of tools to do that, and in the end you get something called a portable output file, and this is actually stable. So you get one of these files for every country, region, customer, and possibly subsystem of your code. And these are similar to the sources of a program, and you put them into the repository. How would such a code look like? As mentioned before, it's a text file. In the front matter, you say, okay, this is a portable translation format, a file for, in this particular case here, the Czech language. And there's also a line in there that says, how many plural forms does this particular language have? We are probably accustomed to a language that has an Indo-European descent, so you have a singular form and we have a plural form, but other languages may have a different opinion on how we express multiple things in a language. And the Czech language has one singular, a dual, and a plural form. So we have to support that. And you have even more tools then to go from this textual representation of a translated file into something that is then merged together. As said, we possibly have multiple subsystems that you can support, and we can also check the context of these files. And this is a very important step in here, because we can now check if the formatting specifications that we had in our C++ source file is also correctly translated into the target language. So this is an important step in the whole process of translation. We want to make sure if we have a valid input, we want to get a valid output from that. And this is how a compiled form of that looks like. We see a bunch of strings in there and references, tables, this kind of stuff. Hence, this is called a machine object file. This is geared to machines to actually interpret them. We as humans don't see this at all, except for this is stuff in the file system. This is standardized, and we will come back to that. I've mentioned the plural forms. Where do these formulas come from? How to figure out if you have, for example, 3 apples or 5 sisters. What is the correct version of plural text that you get out of that. And here comes Unicode into play. When we speak about Unicode, we think about glyphs, code points, encodings, UTF-8, UTF-16, such kind of things. But if you look closely, there's also something like the Common Language Data Repository. This is also part of Unicode, and if we look into that, we see there's a page about plurals and units, and also particular plural rules in there. You're not supposed to read that, you need to know that it's there. And if you dig even deeper, it says, yeah, every language has its own rules and own opinions how this should be done. And we have codes, how we actually designate particular languages, how many categories does it differentiate into, what the rules are, and all these are also governed by particular standards that you can find in the internet. And what does these rules look like? Don't try to read it. In the x-axis we have a time, a number arrow from 0 to something, and in the vertical axis you see different languages. And we have, for example, languages who don't even have a notion of a plural. Most Asian languages don't have that. Here are the Indo-European languages. This is Czech that I've mentioned before, and we have very complicated rules for a language called Breton, something that is spoken in Brittany, and it's quite similar to Irish. Yes. So we can have very simple rules, like the one that you see in lines 1 and 2, for example, Japanese, no plural forms, and in German, for example, it's an Indo-European, we have singular and plural. Czech, we, as mentioned before, a dual, and a very complicated formula for Breton. These formulas are expressed as single-line C expressions, and this is what all these libraries dealing with translations have to work with. Okay. Boost Local implements all this kind of stuff, but I have a gripe with it. It does way too much, in my opinion, because every time you do a call of an individual translation, it not only does the translation, it also does an encoding conversion. And as mentioned before, we deal only with Unicode, so I don't need an encoding conversion. But having an encoding conversion, and I can't deny doing it with Boost Local, I have to pay for a string translation because every encoding conversion involves a string allocation that has to be returned from the call. And now I have to pay for something that I don't want to. And I'm cluttering the heap every time I do a translation. So this is where we step forward 4 more years into the year 2018. And in 2018, I would say, the formatting library, libformat, maybe you know about it, became pretty stable and usable, and I was also a heavy contributor to this library, quite familiar with it. I decided maybe we should ditch Boost format and go with FMT format. We have moved along from C++ 2003 to C++ 14 here. And what does it mean to switch the library? As seen before, we have this separation of the constructor of something that deals with the formatting specifier or the untranslated string, and a couple of arguments as operands into a particular operator. we now put everything into one call. So we no longer template on the character type we want to use in our strings. We now template on the argument types. And this has a serious change in how we structure a particular library. And this is the first time we see something as a type list. In the bottom, in line 1, we see template type name ... ts. This is a type list. It's a heterogeneous sequence of types in there. And all of those who are familiar with this kind of thing would immediately think, oh, this is bad, this is horrible. You have an explosion of template instantiations and lots of code bloat. Do not do that. But libfmt has you covered. We not only have this typeful interface, we also have a type erased interface, and there is no template in there. And the typeful wrapper is just a tiny skin on top of the type erased interface. And this is something that all compilers easily see through, so you don't have code bloat and a multitude of template instantiations that would blow up your execution sizes anymore. And now we can employ a lot of things in the library to do this type erasure kind of thing. And yeah, and to some degree, this is also type classification. And how do we do that? It's kind of a tangent here. We use type-based metaprogramming in the formatting library. What does it mean? We use templates to calculate types. We use partial template specializations to do something like pattern matching. If we have particular patterns, we can use techniques to actually then classify what we are dealing with. We can use overlap resolution and implicit conversion sequences to use these kind of things to actually also do metaprogramming on. This is called conversion-based metaprogramming. In C++17 we had no except based metaprogramming. Everything what's in a signature can be used or abused as something that you can metaprogram on. And the final goal is always we want to do Sphene. We want to constrain our templates and everything in there and use these kind of things to actually change or adapt the behavior of the inner workings of a library or something that we are interested in. So Sphene is always the goal, or we are doing that. But we have to be aware of that. Type-based metaprogramming can become very costly, and there has been an study how costly type-based metaprogramming can be. This is Giel Dues. He was doing this kind of study in 2017 or so. These were the heydays of type-based metaprogramming, and he came up with this list. Sphene is one of the most important, most expensive things that you can do in C++. So you have to keep this in mind if you are doing type-based metaprogramming. It can be cheap, but it can also be very, very expensive and taxing to your compiler. And this is called the rule of Giel. And now we have to go into a tangent here, because I was talking about type-based metaprogramming, and there are lots of functions in there, and we need to speak about what do we mean by that. So if you have a function called f, this is an operator that can operate on a particular set of things that you put into this function, and we get something out of it. So we have a rule how we do this mapping from elements in one set, in the input set, to the elements in the output set. And as mentioned, it can be anything. At school we learned these are values. The function is operating on values. But this is restrictive. This x could be also be, for example, could be types. And we could return functions again. This is all we can do with type-based metaprogramming. And now we do have to look a little bit upon syntax. This is something we see in the first and default example. Use functions which have exactly one argument type, or one argument, and the middle one has two arguments, and we have a set of arguments in parentheses, and these are the parameters to a function that are in general runtime parameters. This is what we do every time, but they can also be potentially valid at compile time. And on the other hand, these angle brackets are arguments to a function that need to be available at compile time. You can't get around them. So we call them template parameters and template arguments and template argument type deduction and all this kind of stuff. But these are just additional parameters to our functions that are known at compile time. And only the context determines which kind of syntax we have to use here. Okay, let's move along. 3 more years. We had more translations. Now we had C++ 17, and we have C++ 20. And in 21, C++ 20 adopts proposal P2216. And I don't expect you to understand what P2216 actually means. It changes the syntax of the format functions that we have adopted into C++ 20 from the formatting library. Now it's no longer FMT format, it's now std format. And in the Prague meeting 2020, we had the same signature as the formatting library had back then, but with P2216 we have changed the signature. And as you can see, it's for the most part the formatting string. It's no longer a string view, it's now a type on its own. And this type has a constructor. This constructor takes the string view from before, but it also has this type list. Do you remember? The formatting library is using the type list, which is a collection of all the argument types that are supplied to the translation, the formatting. And now we have a constructor that knows about the string that we give as a parameter and also knows about all of the argument types that we give to the actual formatting operation. And you see also this particular specifier or qualifier, I don't know, it's probably a qualifier. It's called const eval. And const eval is also something that has been happening in C++ 20. This means this is a function that can only be evaluated at compile time. Beforehand, we had const export. These are functions that can be evaluated at runtime and at compile time if it all the necessary preconditions are fulfilled, but this one can only be evaluated at compile time. And this has an impact. So what does const eval mean to us? And in particular, what is constant evaluation? The name alleges to the idea we are talking about values now. Formerly we've been talking about types, now we are talking about values. And we are talking about constant values, and we can do that at compile time. So whenever the compiler or our translator is reading the source code that they write, it sees the identifiers, the entities in there, it sees the declarations, the definitions, and a lot of more things. It sees also our templates, our template instantiations that they had so far. It pretty much sees everything. And actually, knowing all of this and destroying it and forgetting about it at the end of the compilation is the reason why we have modules today. Yeah, this is the only reason. And if we look at our C++ code, we see lines like this. It's just a random set of lines that you might encounter. And we see a couple of lines here which actually require constants. And this means we have to do constant expressions and constant evaluation in here. So now we know what constant expressions and constant evaluation means. We can look at the full picture of what a compiler does. You should know it. But we have tables in the compiler which handles all the entities that we have seen so far, all the type stuff, but we also have some entity in the compiler which does the evaluation of our constant expressions. Both of these are pretty old. The constant evaluator was called a long time ago constant folding, and it did pretty simple stuff only. But in C++, with C++ 11, constant expressions came into existence and it expanded over time. We have seen the keynote from Hannah just one day ago. You can do so many things at compile time and in constant evaluation, and we don't see an end yet, and everything is just expanding over time, and we can do magic using values and constant evaluation. So let's go back to P2116. What does it mean to have a const eval constructor on a type? Here is the function body of this constructor. This is from the MSSTL implementation. You see a couple of constant expression types in there. We have these num-args and we have this archetypes array in here. And all of these are and must be evaluated at compile time. So here we see a complex constant expressions, and we can use that to check for the format string, the validity of the format string, of the format specifiers in there. We can look at the argument types, if these match up, if this is actually possible at all. And all this happens at compile time. So this means if the compiler says everything is fine, we no longer will experience exceptions at runtime. This is something we want to avoid. If it compiles, we no longer have, for example, a machine no longer working because of an error in our program or a denial of service if we have something on the web. So this is actually a desired property of our code. So with all of this, let's move on another year. We have more translations and another year. And in our company, we were adopting Visual Studio 2022 into production. And this means we also adopted P2216. So what does it mean? That the fallout of doing all this stuff at compile time, Boost Local, at least that part that deals with the inputs, the format strings, is no longer a thing. We can no longer defer the string translations that we are interested in into runtime back. We have to do everything what we need to do at compile time. We still want to do that. We want to mark our strings, what we want to translate. We want to change the strings depending on a runtime value and get the correct translated string in a desired language in a particular company. Here we have Norwegian with one plural form, we have Czech with two plural forms, we have Slovenian with three language plural forms, and we go, for example, up to 5 of them in Arabic. So, if we look at the signatures of this format string that we get with C++20, the constructor is given, it's something that is done at compile time, and what we get out, the string, what we actually want to see in our UI or in our code is a string view, and it's also fixed. So we can't do something with that. So what do we do in this particular case? What would you do? Yeah, this was the situation that I was in. What to do now? Okay, the typical solution, use another overload. If the standard library isn't supplying one to me, I have to come up with my own. And it's pretty similar to what we find in the library, in the standard library. I now no longer have the basic format string. I'm using something on my own, a new type. This is modeled after what we have in the library, but gives me additional capabilities. And in particular, I can choose how it's behaving. And if you look at the lines 4 to 7, we see stuff what we can do now again at runtime, even though the construction takes place at compile time. You don't need to understand what's going on here. If we construct this type, we have this constant time, compile time constructor, and most of this work is actually done here because we defer the checking the validity of our strings to the standard library. This is what's done here. And yeah, here it is. And we can even go further and check, are these strings consistent? If the plural and the singular form that we supply consistent, are the arguments that you supply that determines which language form we are interested in, are they there, or are there too many of them there? And does all this match up to each other, and we can check all this kind of stuff at compile time and give nice error messages if we fail here. And we can go a step deeper, lower, And what we can do, if we really embrace compile time expressions and compile time evaluation, do we really need to store all these strings that they supply? Remember, translation is something we have strings as inputs, and we want new different strings as output. What's required there, this is something like an unordered map. And what does an unordered map mean? We have to calculate hashes and look into these maps. So if we want to get rid of all these strings as inputs, these are always the same. They are required to be constant strings. Why can't we just go a step further and calculate the hash of all these things? These are always the same. And this is what we can do, go deeper and deeper and deeper. If we have the hash, we can figure out what the runtime translated string would be, and we go another step deeper. And now what we actually have to do is just store a number. That's all we need to do in the front end, and we can do all of it on compile time. We don't care about what encoding our strings are in, UTF-16, UTF-8, whatever. In the end, we want just one number, and it should be a stable number. It's always the same. We only look at the meaning of our strings, but not at the encoding. This is the only data member that we actually store. And this is the only part in the front end where we have to do something at runtime. We get our tables. We have this number. We know what cardinal we want to supply if we actually do. And now we can look up. This is what string translation actually means. Here we go from the compile time world into the runtime world. This leaves us with 3 questions. Question 1, which of the arguments that we supply is actually the one that determines the language form that we are interested in? Question 2, how do we get the value? And question 3, these arguments may also require translation. Which of them need to be translated, and how do we do that? Yeah, the third question is actually an easy one. We have seen we have type-based calculations. We can map our input arguments into whatever we want in type-based calculations. And this is something that you do here. We return a function. And this function is, what kind of function that you return is dependent on the argument type. Now we pattern match on the argument type, get a function out of it, and this function may do a translation or may not. This is type-based metaprogramming. And the other 2 questions can also easily be answered with P2663. This is package indexing. It's part of the draft in C++26. And P2996 reflection. This is something we can hopefully agree on next week. But we have this is simple. This is really simple to implement using these particular proposals. But unfortunately, this is C++26, hopefully. And this was something that I had to figure out past year. So I had to come up with something that looks like we have C++26, but is actually C++20. So we come back to the notion of heterogeneous sequences. I mentioned the type list. And how do we deal with type lists? Yes, Since C++17, we use folds, and there's a seminal paper from the past century coming from functional programming. Folds are awesome, and you can do pretty much magic with them. So how can we use that to figure out what the answers to questions 1 and 2 are? What am I speaking about? Let's compare homogeneous sequences like a vector of values and heterogeneous sequences like a type list, a list of types. And we have a subset of algorithms that we can use. We can use projections, we can use predicates, and map them to the output types that we can provide. For example, we can map them to an index in the sequences. We can map them to a Boolean expression, or we can map them to nothing, like for each. We are just applying a function. And we can do just the same with heterogeneous sequences like type lists. And now you see why we had this tangent. All of the arguments go into angle brackets instead of parentheses, and which means we can handle these type lists at compile time. The return types and the return values are just the same. We can still apply projections, we can still use predicates. So let's try to answer the first questions. We need something like a ranges find if, but on a type list. How can we do that in C++20? This is something like we are looking here. So the first answer is, what should be the return value that we give if we find nothing? Okay, this is the return value of no index found. This is our predicate. In this particular case, I want to figure out which of my types is actually the one that is the marker for the plural. And this is how I want to use it. I give the type list from the list of types that I supply to the formatting, and given the predicate, I want to find the first index in this list that is actually giving me the plural form. How do I do that? Okay. Easy step, first step. If I find nothing, if I supply nothing, I return no index. Okay, unit test 1, green. Next one, a little modification, nothing changed, still green. Now I give the predicate and the type list. Okay, I do a fold expression here, and I apply the predicate. Remember, the predicate is mapping from a type to a Boolean value. I can fold over it and get a Boolean. And if I return the same return value as before, I now have 4 unit test cases. 2 of them are green, 2 of them are red. I can expand on the predicate and return via a ternary expression true or false explicitly. Nothing has changed so far. I can expand one step more, and I can number all of the elements in my type list, going from 1 to n. Still nothing has changed. And in the last step, as soon as my predicate hits, I get a bool out of the predicate. I go into the first leg of the ternary expression, and instead of writing bool, I'm just returning the result. And this is the index of the entry in the type list. And now all of my 4 unit test cases are green. It may sound a little bit strange in the beginning, but this is actually something that we can do in C++ 2017. Okay, strange, but pretty much doable. The next, how do we get at the value at this particular argument slot? We know these are references. On the other hand, other side of the reference are objects. We can take the address of an object and we can erase the type and go to a number. This is the uint pointer type here. We can take all of these objects and initialize an array, an homogeneous array of these numbers. We got the index from the step before. We can index into this array and undo the type erasure again. We know what it is. It was our predicate before. We can look at the value, and now we know what kind of value has the user given to us. So, question 2 is answered as well. And the best thing is, this is valid code, no undefined behavior in there. And to the third question, this type-based metaprogramming that is used here, we use a struct as a function. We have the template argument or template parameter as a function parameter, and we return a tuple of a type and this function, and this is what we have been using in the lines in the slides before. Here it is the general case. Here it is for everything that we have marked as a translatable string, and this is the case where we were supplying the plural value, the cardinal. And we call this pattern matching. There's a proposal 2688, also hopefully discussed next week. So we see what we can get out of it. So with all of this in place, I went wild. We can do so many kinds of things at compile time. What if I can drop the back end of Boost Local, where all these tables are managed, and also implement all of this stuff at compile time? And if I've done everything right, can I perform an integration test? And this is the code. This is my test function. If I supply the contents of such an MO file that we have seen before, and I give a particular cardinal, like this one, 1,000,000, and can I check if the output of a translation with these particular tables and this particular cardinal to have a certain result? And I want it to be a white string. What does it mean? I not only check what's going on in the compiler. Remember, constant evaluation is performed in the compiler. I also have to involve the build system, because this is what I have. 3 strings that I want to be the input of the translation. This is marked as translatable. These tools mentioned before extract these 3 strings as a particular translation. compile them into POs. And to make things a little bit more complicated, I was putting all of the strings that I have in this machine that are marked as translatable also as PO. I can merge them into a compiled this MO file mentioned before, massage it a little bit more, and inject it into my source. There's this embed kind of thing that Jean-Hy was coming up a couple of years ago. I have an implementation here as a module to give me back the bytes from the bin file that I had in the build system as a compile time constant. Actually, it's an array. And this is something that I put into my test function, and I'm loading these bytes, and contents is seen at the right, into these tables. I built these unordered maps at compile time, optimize them for speedy access into them, and this is done here. And then I can actually call the translate function. Formerly it has been a syntactic marker for the get text. Now I've calculated this number seen before. This is the representation of these three constant strings. Ask for a translation given a particular cardinal and check if the output is the correct one. And if it is, line 19, this is the second constant evaluation in this whole integration test. It should be fine, and actually it is. What does it mean? I can do testing at compile time, and this is very much code that is tested here. It's actually a little bit more 3 million evaluation steps in this test that is performed in the compiler to do this test. And this means, as we learned from HANA, we have made sure that all our code does not contain any undefined behavior. This is a property that we want to make sure in our code. Now we can, even with testing. And even better, we can not only test at compile time, we can perform the very same test at runtime. Now I'm no longer supplying the contents of the MO file as a compile time string or array. I can do exactly the same what I would use in our machine. I store the MO file into the file system, give it out to our customers, and do everything what I want to do at runtime just as well. So these are a couple of resources that you can look up if you're interested in this kind of stuff. I'm still destined, or I hope I can make this stuff available as a GitHub repository. I'm not sure when this will happen. I'm too busy with too many things. You can attest to that? Yes. So don't be too eager to look at this non-disclosed GitHub repository, but maybe this is something that I want to bring to the committee, because now we have a standardized version about how we should do translation. Maybe a library like that might be interesting to the committee. Actually, this gettext thing was formally alluded to in a proposal by Victor. You should have probably read it. Okay, this is all I have. Thank you very much. Yeah, pretty short on time. Maybe you have one or two questions, if there are any. There's
one question, well, actually two questions from Martin Röseler. online. What artifact is sent to a translating company?
Excuse me?
What artifact is sent to the translating company, to a translation service? Like, a linguistic company that translates to...
It's not only the company, a translation company who does it, it's actually our customer. So we give them the extracted strings. I've mentioned the output from the scanning process. We can give them to our customers or to professional translators, and they will just give us the translated tables back. These are the PO files that I've mentioned before.
There's a second question from Martin, and that is, how do you handle non-text translation, like floating point going from 3.14 in English to 3.14 in German?
Yeah, we don't do that. Translation doesn't handle these kind of situations. These are pure strings.
Okay.
We don't have an interpretation on the context of these strings. The only interpretation that we have is how do we actually translate plural forms correctly.
Okay, thanks you. I have a question about the utility for embedding the binary files.
Okay.
Is there a reason why you didn't use the C version? There's a C #embed.
Yeah, there's a very good reason. Our compiler doesn't support it.
Can I have dinner?
Yeah, that's the whole reason why.
Yeah. Another question maybe. You showed the find if with the fold expression. Is there a reason why you didn't use the like the normal, let's say normal recursion of the template parameters list? It's easier to read, but probably maybe less performant for compile times.
Yeah, you mean the recursive expansions of templates?
Yeah.
First of all, I don't like that. And the second answer is, you've seen the rule of heel with all the things that you have to do if you use type-based metaprogramming. And this recursive expansion of templates is template metaprogramming. Try to avoid it as much as you can. So don't do a recursive expansion if you have better ways to do the same thing. This is why I'm using fold expressions.
I have a linguistic question more than a C++ templating question. In German, for instance, we have the singular for apple is Apfel.
Yes.
In all cases. And
yeah, singular is Apfel and plural is Äpfel.
Äpfel. But I'm sure there are languages out there where there are different plural forms for the same quantity depending on the case of the word. So whether it's nominative or accusative or genitive or whatever. How is that handled? Or is it?
It doesn't have to be, because the same case had to be in the original text. And if you translate, for example, a particular word and a particular form from the source language into a target language, you know what you are looking for, and you can handle it in the translation. You don't have to handle different varieties which are not different in between particular cardinals that you supply. Maybe I've misunderstood you, but I think this is actually what translation does in almost on all translation systems that I know about.
Okay, I'm just even thinking of the articles, articles in German.
Yeah.
You have what? Der Apfel, ich gebe dir den Apfel. And again, when you translate that one into, when you make it plural, it becomes ich gebe euch die Äpfel. And it's den goes to D. but
Yeah, but
or is that? Oh, that's
but there
also
are rules
possible.
behind that, and these are fixed.
But okay, yeah. Okay.
Is that you don't translate individual words, you always translate complete sentences.
Yes.
And then you can't just place sub-sentences into existing structures because that doesn't work.
And this is the reason why we
Okay.
don't want to have too granular translations. For example, what you get if you use cout and all the streaming.
Okay, so you're avoiding my problem, which is excellent.
Yeah. If you want to give correct translations,
Yeah.
you need to supply context.
Okay.
And a larger sentence is a better context than an isolated word.
And I guess that's why you can only support one plural quantity in the translation.
I can support one plural quantity in a translation for the formatting string,
Yes.
but I can supply multiple cardinals for the individual arguments as well. This is what the library is actually capable to do. So I can form a string where you can say the basic translation is, for example, French for Belgium, and you supply parts of the strings. One is Norwegian, one is German, one is Arabic, and supply cardinals, individual cardinals to them. So this is pretty versatile. I didn't bring the examples here because it would be a much longer talk, but you can actually do that.
Okay, thank you.
Welcome. Any more questions? Then I would say session is over. Thank you very much.